some of you, if you've had a psych class or a social class or something like that, but what we can do is, we talk about this 16 being the average distance a data point is from average. On average, it's how far data points are from average. So if you took all the distances and added them all up and divided by how many there were, it's going to average out to 16. But when the data is bell-shaped, where are the majority of the data points? Close or away from the average? Right. And now here comes the best part. Let's add and subtract that 16, just like Carly just said. So the average is definitely at negative 15 pounds, correct? Let's go out 16 pounds in both directions from that 15. So if we come up to here, it's going to be just on this side of 0, isn't it? So if we do x bar plus s, one standard deviation up from average, what's that value going to be down here? That'll be 1, right? Negative 15 plus 16 gives us positive 1. Some of you might be wondering why the hell I'm doing this right now. The quick answer is Carly told me to. The better answer is there's a point to it. There's a point to it, I promise you. Let's go down. Negative 15 down. 16 would essentially put us right here. And that would be x bar minus s, yes? And that would be negative 31. Get my math right. We're rounding all this off, yeah? Because we rounded the 15 to the 16 to 15 to 16. Okay, negative 31. This range of values right here is called one standard deviation. I want to apologize for all statisticians everywhere. I do, because there's a confusion in that phrase, standard deviation. I now have used the phrase standard deviation to stand for two different things, haven't we? Number one, it is this number. And now I'm talking about this range of values from negative 31 pounds up to 1 pound is one standard deviation from me, from the average. You see how they're related, but they're slightly different? One of them is one number, the 16 pounds, and one of them is the range taken by adding and subtracting that to both sides of the value. You see so you'll get used to it, I promise you this. You'll get used to that. But I apologize in advance. I wish we called them something else. Like, I wish we called this something else. Like, I wish we called this the variance, honestly. But we don't. We have to get used to that language. So the standard deviation is that average distance from average. But when you add and subtract it, you get a certain number of standard deviations. A certain number of standard deviations. How much data is in there? A lot or a little?
No, a lot.
Most. Good. A lot. Most. Count it up, friends. Count it up on the on your actual raw. Something you usually can't do because you don't have the raw data. But since we do, look at your data sheet and count up how many data points are actually within negative 31 up to 1 pound. And if they land at negative 31 and 1, it's your choice whether you want to include them or not. Because technically speaking, that's getting so close they could go either way. See that? We cannot. How many are in there, friends? What do you got? 24, 25? Either one of those is fine. It depends on whether was there a negative 31 or a 1.
Yeah.
It depends on whether or not you include them. Your call. We'll call it 24. Okay. That's definitely the majority, isn't it? I mean, 35, half of that would be 17 and a half, so we got more than that. So that's the majority. Good. Fantastic. I want to come back to that momentarily. But I want to keep driving this point of standard deviations. Because most statistics don't deal with just one. The most popular number of standard deviations is actually 2. Now, that you might not know why right now, and that's okay. Don't worry about that right now. It has to do more with the 244 idea. But could we form 2 standard deviations from average? In much the same way we did 1. I think so, yes? Take the standard deviation again and add an additional 16 and subtract an additional 16. So instead of stopping at 1, we're going to go up to what? 17, which would be x bar plus 2s. That's this guy. Let me make that a different color. Orange. That'll be good. Is that okay? Can we see that okay with the orange? Okay. Are this, oops, that's not a straight line. Are we okay with the symbols x bar plus 2s? That's just algebra. Trying to put variables in instead of putting the numbers down here and the variables up top. If we take 16 more off of here, we get the negative 47.
Yes.
All right, good. So what's that going to be? It's going to be somewhere 1, 2, 3, somewhere in here, I guess.
Now what's the reason we're doing this again?
Give me 30 seconds. That's a great question. That's a great question. No. There's a predictability that Pat actually asked about before he left. He got tired and left. He's hell with this. There's a predictability about that. The reason I like this data set is because it's bell-shaped. And there are lots and lots and lots of bell-shaped data sets out there, and they all have a commonality. And we're discovering it, if you will, right now, but it has to do with setting up these range of values first. Some of you have learned this before, I think. But hold that thought. Tell me your name one more time. Patty, thank you. Great question. And this is kind of cart before the horse a little bit, but there's no other way to do it I found other than to put the cart first, let the horse catch up. I mean, I'm not calling you guys horses, I'm just saying that this is kind of a little bit backwards way of doing it. But so far? So this range of values now, from negative 47 to 17, would be called 2 standard deviations. And that goes negative 47 pounds up to 17 pounds. How much data we got in there? Even more most. I like that, more most. How many? Count them up. Count them up. How many data points in that data set lie between negative 47 and 17 pounds? How many of them lie between negative 47 and 17 pounds? What do you think? Negative 47, 17 pounds. I'm getting a good idea for a quiz in class on Tuesday. This might actually be good.
34.
I got 34? And you can, there's nothing magical about the numbers 1 and 2. As a matter of fact, I think if you go out 2/3 of a standard deviation, I think you trap roughly half of the data, I believe. We'll come back to that later in the course when we have more software to play with. You can go out as far as you want. You've got the 3 standard deviations. See the logic in 3? You would just add and subtract 1 more s on both sides. Linda, go ahead, please.
So how did you get the 34 out of the 34?
Nick did. He counted them. He just went into the data. He just went into the data and he counted up how many data points were between negative 47 and 17. Oh, Nick, I think it's 33.
33.
I think it's 33. There's a 21 outside on that side,
Oh, yeah.
and there's a 58 outside here. So I think that's going to be 33. Yeah. And I mean, depending on how you round, we might not get the exact same results. We're gonna get ish in the ballpark. And we can go out to 3 standard deviations. How far down would 3 standard deviations start? Right, 16 more down, which would be what, negative 63? And it would go up to 33, I think. Good. How much data is between negative 63 and positive 33? All of it, 35 out of 35. Now, what I'd like you guys to do, turn those, if you will, into percentages for me. 24 out of 35. I want to bring it back to a discussion that we had about 45 minutes ago, talking about what percentage of folks lost weight. I love the idea of saying 80% lost weight, but I don't like the fact of losing, yeah, 80% lost weight, but how much weight did they lose? I think we're getting close to tying that idea together here. So what's 24 out of 35? Is that like 2/3?
68.
68%?
69, yeah.
How about 68 and a half?
68 and a half.
That way, somewhere 2/3-ish. 2/3-ish. Yeah, ish. Somewhere in there. With a small data set, you're going to have quite a bit of flip-flop back and forth. So, how about 33 out of 35?
94.
94%? And you already gave me 1. If we go on the 3 standard deviations, you pick it all up. It was 100%, wasn't it, decimal-wise or percentage-wise? Now, Why am I getting so excited about this, other than the fact that I get excited about this crap all the time? But, Carly?
Because 2 standard deviations, the window accommodates, or it excludes the outliers.
Nice! Good use of the word outliers, very nice. You took it way past where I thought you were going to take it. Thank you, my friend. Yes. There's a topic in this class, we'll get to it soon, i.e. next week, called outliers. And it's one of those wonderful, wonderful ideas that is often talked about and never really discussed quantitatively. So can I hold it, if you don't mind? Before we get too far into that, I want to hold it. But that is the most common statistical definition. If your data is shaped like a mound, like this is, mound-shaped data. I think mark it. Yeah. If you've got a mound-shaped data, if you go out 2 standard deviations on the mound-shaped data, anything outside of that is too big or too small to be considered within the mound. Now, technically it is within the mound, it's in the tails of the mound, but it's considered a fluke occurrence. Remember how I said earlier, if you flip the coin 13 times, you got 13 tails, you haven't proven that the coin's broken, you may have just flipped into the tail. And then those tails happen, obviously, there are data points in the tail. They're just not typical, atypical, which is the definition of what an outlier is. Well, let's come back to that. Let's tie it back to something more recent. Remember we liked the 80% plus or minus before, the discussion about how many lost weight? Why are these percentages even more powerful? Jolene?
So you can say out of this study, roughly 68% lost more, or between 0 and 1 pounds.
Now you can assign a percentage to an amount of weight lost or gained. You could say roughly 2/3, 68.5%, 69%, whatever you guys were saying, somewhere in the neighborhood of 2/3 of the weight loss participants lost between 31 pounds and essentially 0. That's a 1 pound gain. That's powerful to know, because now you have a quantifier, not just a 1 or a 0. Yes, I lost weight. No, I didn't. Yes, I lost weight, and here's how much. 2/3. There's a 2/3 chance you lost between 31 pounds and or gaining 1 pound. That's important to know. That's important to know. Can you go out to 2 standard deviations? What does look? Now it looks like meaningful. When you go out 2 standard deviations, now you can say there's a what percent chance? A 94% chance that you're between -47 and +17. Once again, you've increased the probability, you've also increased the range, and that's when people might start going, that gain of 17 pounds makes me nervous. But then they pop back to the 1 standard deviation and go, yeah, but 2 out of 3 lost a chunk of weight. You see how you're getting more from the data than just the number 16 and just the number -15? What I'd like to do is summarize this. This is actually called, this happens with all bell curves. This is the idea I just had while you guys were talking. I'm going to make an in-class quiz, I think, for Monday or Tuesday that allows us, I want to go find some other data sets that are bell-shaped. I was hoping to use your height, but they're not going to work. And we'll try to put that down and derive this result from them as well. There is something called, I think your book calls it the empirical rule. I think most statisticians call it that too. Let's put it over here. Now, the proof of this is going to have to wait, unless you want